organizers for inviting me to this workshop. So my talk is about Goncharov conjecture. So like Goncharov conjecture is about how you can compute like case theory rationally using some explicit complex, maybe not so explicit, which is connected with functional equations for polylogarithms. And so my approach would be to do some more or less explicit computation using like presentation of case theory using algebraic cycles. Okay. So first of all, I would like to introduce some conventions. So like first thing is that I work in characteristic zero. So like just for simplicity, I think it can be generalized, but like this is my assumption. And second thing is that everywhere I work rationally, so like ignore any torsion, and I implicitly assume that like any abelian group is tensored by Q. So I will not say it like explicitly, but I assume it everywhere. Yes. Okay, so for a field F, I define by Kn its algebraic case theory. Then we have action of Adams operators, and so denote this agent space. Yeah, this is standard notation just to recall it. Yes, so we know that like algebraic case theory is sum of the space over all G. Yes, so if you have any questions, please ask. Yeah. And I would like to recall some like classical statements. Like in some cases, we can compute algebraic case theory, and actually all these statements were known when Goncharov formulated his conjectures. So basically, it is two results. That is like a statement about Milnor case theory and Suslin theorem. So first, I would like to recall Matsumoto's theorem. So we have a multiplicative group of my field. Then I take exterior power of multiplicative group and take quotient by so-called Steinberg relations. So this is A which 1 minus A. Yes, this is a classical statement that like we have explicit presentation for second case theory. Yeah, and in some sense, and like the goal of Goncharov's conjecture to like generalize this result to and so I need to give very important definition. That is block group. Block group already appeared in this workshop, but I want to recall. So what is block group? We can think that like block group is like abstract dilogarithms. So we take a functional equation for dilogarithm, namely Bloch-Wigner dilogarithm, and try to like define something similar over any field. So we take free vector space generated by all points of my field, not all, like all without 0 and 1. Yes, so this space is just like formal linear combinations of all elements of my field. And then I take quotient by the following relation. So this is Abel 5-term relation for dilogarithm. So if I have 5 points on projective line, then I can delete one of these points, compute cross ratio, and consider corresponding element in this like vector space. And so it was stated that like Bloch-Wigner dilogarithm vanishes on these relations. And we can define this group. Yes. Okay, and I want to like recall definition.
1 second. Can you go back one slide?
Yeah. Previous.
Yeah. Why are the elements in P1 like the original elements were just an F, right?
Yeah, but like if you have 5 different points, then cross ratio, it is like non-zero and not equal to 1. So like, it will be well defined.
Okay.
Yeah, it's just like you can take that like.
So I see. CR is a map from P1 to the 4 2F.
Yeah. Great, please. Yeah, and so we can define a polylogarithmic complex in weight 2, which is also called, I think, Bloch-Suslin complex. Yeah, and so like this complex actually reflects like nature of the logarithm, because like this group B2 describe functional equations for the logarithm, and actually this differential describes differential equation for the logarithm. Yeah, so this is very simple formula. It is obvious that co-kernel of this map is Milnor K-theory, yes, second Milnor K-theory. Yeah, and the kernel, yeah, it is something. And well, it is called, Suslin called it block group, but now we call this we call this block group. Yeah.
Some people do.
Yeah. Yeah, and so like non-trivial statements that irreducible K3 can be computed as first cohomology of this complex. Yeah, and I would like to generalize this statement. Yes. Yeah, and I want to recall also that like there is statements that we can find Milnor K-theory as a piece of algebraic K-theory. Namely, if these indices are the same, then like result of Suslin, Nesterenko, and Totaro says that we get exactly Milnor K-theory. And it is interesting that like there were two proofs of this result. Suslin and Nesterenko computed some group homology, but Totaro like did some computations with Bloch-Chow groups. And in this sense, I will generalize approach of Totaro. Yes. Maybe you have some questions. Okay.
So sorry, for the n, in the formula is m or n?
M, right? On the right hand side,
M and M is.
Well, okay, yeah, m is equal to n. Yeah, I can write. Like, can I write on this blackboard? Can you see this presentation? Yeah.
Oh, you should probably lower it.
yeah.
What?
You could write on it if it's left.
Yeah.
Well, it is.
Okay. Yeah, so the next definition is a little bit less straightforward. So Goncharov defined polylogarithmic complex in any weight, and this complex is connected with truncation of Goncharov's complex. So I don't want to define in the full generality. I define just the very end of this complex. So in degree m, we have exterior power of multiplicative group of my field. I like recall that everything is rationally. So this is vector space over Q. Then I consider the following group. This is tensor product of block group by so times also exterior power of multiplicative group. The map is given by very simple formula, namely this one. So this is straightforward generalization of weight 2. And we see immediately that co-kernel of this map is exactly Milnor K-theory, yes? But also I need another so part, yeah, so this is defined by very simple formula. It is just free vector space generated by all points. Yeah, so like I need this term in order to compute cohomology like here. So I need take kernel of this map, modular image of this map. Yeah, actually we can like replace this group with third block group, but as I don't need like a homology here, I need a homology only here, I can just define as a free abelian group. Yeah. Yeah, so this is some explicit complex given by explicit formulas. Only non-trivial like notion here is block group. We need to know what is block group. Yeah, but of course, like compute this cohomology is not so easy for any field. But in any case, definition is very explicitly, very explicit. Yes. Yeah. And so this group sits in degree m, this group sits in degree m minus 1. Okay. Yes, and by definition we see that cohomology in degree m is Milnor K-theory. Yeah, so and I want to state my main result that this K-theory is isomorphic to cohomology of this complex. Yeah, so we take cohomology in this place. Yeah, and I can prove that we get K-theory. So, yeah, an approach is that we will present K-theory as high Chow groups. So that is some group which is defined using algebraic cycles. Yeah, and we will do some computation in this group. Yeah, so here is some discussion, namely, I want to reduce the statement to algebraically closed field. It is essential for my proof that field is algebraically closed, because otherwise I just cannot define some like very important objects. They cannot be defined for any field. Yeah, and the main statement I need is Galois descent. So Galois descent says the following: if you take K-theory of algebraic closure and take invariance under Galois group, then we get exactly Milnor K-theory of my base field. And it is of course important that I consider everything rationally, because non-rationally this is not true. And so if I somehow can compute this Milnor K-theory for, not Milnor, K-theory for algebraically closed field, then I can recover like K-theory for any field. This is like, yeah. And another important statement is that actually this cohomology group also satisfies Galois descent. And actually this is quite non-trivial statement. So this is this was proved by Daniil Rudenko in his PhD. Yeah, and the proof quite complicated. Like idea is very simple, but we need to like prove some relations in polylogarithmic complex, and this is actually quite complicated. Yeah, so we need to check a lot of relations. Yeah, and it is interesting that, yeah, so starting from here, I assume that field is algebraically closed. Yeah, and interesting thing is that Rudenko's result rely on Suslin's theorem. What is the reason? Reason is that for a polylogarithmic complex in V2, the only way to prove that this complex is homotopy invariant is to use this Suslin's theorem. Unfortunately, there is no elementary proof. So like we have generator relations, but it is like not clear how to prove it. Yeah. And so if I want to prove previous theorem for any field, this theorem, I need to rely on Suslin's theorem. Yeah. But if I want to prove it for algebraically closed field, then the proof is independent. So we can define K-theory using high Chow groups, and then I can don't use even definition of K-theory and prove that high Chow groups is isomorphic to this polylogarithmic complex cohomology. Yeah. Yeah.
Isn't this thing related to the fact maybe that for algebraically closed field, you can see homotopy invariance more directly, maybe by expanding?
Yeah, this is like explicit formulas. Yeah.
So in that case, you can prove it without Suslin's result.
Yeah, exactly, yes. But for any field, this is not clear, yes. So like we need to write generators of block group for function field of over base field, and this is quite difficult. Yeah, you need to write some explicit relation, but like, so for example, I tried, and so yeah, some problems. Yeah. Okay. So I assume that F is algebraically closed field and of characteristic
What
zero.
is Suslin's theorem?
What?
What is Suslin's theorem? Oh, the one from earlier? Suslin's
Suslin's theorem says that cohomology in V2 is K-theory, and we know that K-theory is homotopy invariant. Yeah. Like.
Just that the m's part is Milnor K-theory, that one?
No. About K3 irreducible.
Oh, that one. Oh, yeah.
Yeah. I don't want to go to detail, just want to say that there is a reduction, and actually what I prove, I prove for algebraically closed field. Yeah. Okay. So, like my approach is that, so we have K-theory, and I want to compute this K-theory in some like explicit terms. And so I want to use high HO groups. And to use it, I want to define it. Okay, so what is high HO groups? The idea of high HO groups is like when we have topological space, we can define singular homology. In algebraic geometry, we can try to do something similar. But if we consider just like like affine space and all regular maps are not enough. And so we should consider something like correspondences. Correspondence is something like multi-valued map. Yeah. And so if instead of continuous map, we will consider like algebraic cycles on the product, then we can do the similar thing, so we can like restrict on faces. And so we get some differential similar to like definition of singular homology. Yeah. And so I want to give definition. So I will consider algebraic cycles on affine space. Yeah. And so what is algebraic cycle? Algebraic cycle of some fixed dimension is just formal linear combination of irreducible subvarieties. Yeah, so I take some subvariety and take linear combination. Like I don't know, I have plane. Yeah, and I take one curve with some I don't know coefficient 3. Yeah, take another curve, something like that. Yeah. Subvarieties is a formal linear combination of subvarieties. Okay, and I need some notion of generic position. So, like, first of all, a face is subvariety given by some number of equation of the form. So this is analog of boundary of n-dimensional cube. So if n is equal to, so faces given by first of all these lines, and second intersection by these lines. Yeah, so this looks similar to just a square. Yeah, and in general I get something similar to n-dimensional cube. Okay. Yeah, and I need notion of general cycles. What this means? This means that cycle should intersect any face in expected dimension. Okay, so what is admissible and what is not? Like this one is admissible. This one is not. And this one also is not. Because cycle of codimension 1 shouldn't intersect point. And similarly, cycle shouldn't lie in the codimension 1 face. Yeah. So this is picture. In general, I will get something similar. So some sort of general position. Why we need it? Because we need to intersect cycle with space, and we should get right dimension. If I intersect this cycle with this space, I get something like wrong. Okay, and I denote a group by ZR of n, a group of admissible cycles on n-dimensional affine space of dimension R. Yeah. So I have map. I can intersect my cycle with face. For example, when I intersect this cycle with this face, I get this point. When I intersect with this face, I get this point. Yeah. And so I can define the following chain complex. So this complex consisting algebraic cycles, and differential is given by sines sum of a certain an intersection with faces. Yeah, like for example, if I have this cycle, I get cycle in one-dimensional affine space, like something like maybe 2 points, 1 point with plus and second point with minus. Yeah. And it's easy.
Isn't there a third point because you intersect the line, the horizontal line labeled by 0?
What? No. I take this cycle.
Yeah.
This cycle intersects this space in 1 point.
Yes.
And here's this point.
Yes.
Yeah. Like, do you agree?
Doesn't it intersect your faces in 3 different points?
Yeah, thank you. Yes. So, yeah, something like that. Yeah. Thank you. And it's not difficult to prove that square differential is 0, just as we do in like singular homology. Yeah, because like we get some place in codimension 2 with 2 different signs, something like that. Yeah. So yeah. And there is 1 point that I like. It is not written, but like I assume it when you define. Like you can define simplicial singular homology, and you can define cubical singular homology. This is version of cubical. And when you define cubical singular homology, you need to take quotient by so-called degenerate cycles, because otherwise you don't get like right cohomology of point. Yeah, and so I do it, but it is like implicit. I don't try to, too many formulas, but like it is not very important actually. Yes. Yeah. And there is a theorem of so proved by Bloch that case theory is isomorphic to homology of this complex. Like and I use like grading as in motivic cohomology, but like there are different. Okay. And so. Yeah. So here case theory, and this case theory rationally isomorphic to cohomology of these higher Chow groups. So there are some indices. As usual, it's like not very easy maybe to understand like why you should write this here, but like so this is theorem by Bloch. Yeah.
I think Bloch writes a Z rather than CH. So CH is homology, whereas Z is the cycle.
Yeah, Bloch used like different notations. This is true, yes.
So elements here are represented by something in AM? Is that the indexing of dimension?
No, M is like here motivic weight. So this is N. So these cycles live in n-dimensional space. So dimension of my space is indexed in case theory. Yeah.
And M is the dimension of the cycle?
No, M is codimension. Codimension corresponds to weight. Yes, this is
So can you explain like why it's 2M? Like
sorry?
Why is it 2M and not like M? Like the cohomological grading, I guess. Can you say something about like why the shift is that way?
I don't know how to explain this formula. How I think about it is like. Okay, I think this is not important, this is just like some convention. Okay, so I want to explain idea of my proof, and the point is that this proof doesn't much depends on the value of M. For any M, the proof more or less the same. Yeah, and so I want to explain the case when M is 2, because of course this case is easier. Yes, yeah?
Can you show the previous slide? Do you want to swap n and n on the right-hand side, maybe? 2n minus n?
Yeah, this is correct.
Yeah, but it's written as 2n minus n.
Yes.
I think it's maybe the other way around.
No.
Okay.
Yeah, because this is weight. Yeah. But it's always difficult to like remember. Yeah, and so in case M is 2, everything is... so I want to write this complex explicitly. So here, I just take points on a affine plane. This one is curves in 3-dimensional space. And here, surfaces in 4-dimensional space. The differential is intersection with spaces. Yeah. And so I need to compute cohomology here. So the point is like cohomology of this Bloch-Suslin complex in first cohomology should be connected with algebraic cycles in three-dimensional space. So here is statement. Yeah, and why I won't try to explain what is connection between like curves in three-dimensional space and the logarithm.
I'm a bit confused why your chain complex goes up in dimension, where when you defined the differential, it went down in cohomological degree.
Well, it's this in cohomology degree 0, this is 1 and this is 2. Yeah, it is cohomology co-chain complex. Differential increase.
Yeah, your differentials went down in the R.
Yeah, but you need to define like in which degree this lives. Yeah, this is not dimensional space. This is defined.
It lives in degree R. Like.
No.
Slides.
No, it is not.
Go back 2 slides.
Yeah, it doesn't live in degree R. In degree M minus R. Yeah.
I think you might have swapped something there. Well, I mean.
Yeah.
Oh, this sits in degree. I see. Okay, thank you.
Yeah. It is a little bit difficult.
I get it.
How to understand in which degree it sits, but yeah, it is like it should be compatible with like degree in polylogarithmic complex, and that is why I like little bit change grading.
Okay, thank you.
But in any case, here it is like definition. So surfaces in degree 0, curves in degree 1, and points in degree 2. Yeah. So. Okay, I can draw it like surfaces in curve like x in three-dimensional space and just point on the plane. Yeah. And I want to make a little bit more explicit version of my result. So idea is the following. High Chow groups consisting of all algebraic cycles. Not admissible, but there are a lot of cycles. And it turns out that I want to like take quotient by some like not very interesting cycles. So I want to find certain acyclic subcomplex in high Chow groups, so that the quotient together with truncation give me exactly a polylogarithmic complex in weight 2. This is quite very natural. Yeah, because like when you have two complexes, they are quasi-isomorphic, it's not necessary that they are isomorphic. And so I want to somehow modify it to get just isomorphism. And it turns out that if I take quotient, I already get polylogarithmic complex. So I don't need to modify like Bloch-Suslin complex. I only need to like kill some cycles, some in some sense not very interesting cycles. Yeah. And so almost by definition I get exterior power of multiplicative group. This is very straightforward. But here I take curves in three-dimensional space, modulus certain relations. I will write it, they are quite easy. And modular image of the differential. So I get like description, not cohomology, but Bloch group in terms of these algebraic cycles. Yeah. Map is very explicit, however, neither injectivity nor surjectivity is not clear, is not obvious at all. Well, my field is algebraically closed, but nevertheless, injectivity and surjectivity are very non-trivial. Yeah. Yeah.
Are you going to say what MF2 is?
What?
Are you going to say what the subcomplex is?
Yeah, I will define. To define this complex, I need somehow to like present algebraic cycles. To write some equations for algebraic cycles is not very convenient because they are not of k-dimension 1. And so I want to present it in parametric way. So if I have some algebraic variety together with some functions, I can consider the corresponding rational map from Y to affine space and just take image of this map. It is just like parametric presentation, as like in school we have like parametric presentation of some curve or something like that in differential geometry. Yeah, and this is something very straightforward. The only thing is that I presented so in little bit maybe strange way but the point here is that differential in high-Chow groups for this cycle is connected with divisors of function f1 and so fn. So in a sense, I replace points 0 and 1 to the point 0 and infinity, because 0 and infinity in algebraic geometry connected with divisor. Yeah. And there are some conventions that there is some degree, I need to multiply by degree, but this is like not very important. So this is just like cycle parameterized by y, and f1, fn, it just coordinates on my n-dimensional cube. Yeah? So they parameterize map from my y to this n-dimensional affine space.
Sorry, what is x?
Sorry, what?
What is x? Dimension?
Oh, it's like n.
Is it y?
Rational function.
No, that's not it.
Right.
On the bottom right.
Dimension of x.
This is the
X is y, yes, x is y. X is y. Yeah, so this cycle can be contracted. In this case, this is 0. It, like, if the image of curve is point, then this is just 0. Yeah, otherwise, this is some integer number times this cycle. Okay. Yeah, and so I can define my this is my complex which I want to like contract. So in degree 2, we have just points on a fine plane, yes, and we should take exterior power of multiplicative group. And I just write relations for exterior power of multiplicative group. First antisymmetry, and the second multiplicativity. These two relations define multiplicative group, exterior power multiplicative group of field. Yeah. In degree 0, in degree 1, I want to define something similar. So first relation is antisymmetry, and the second relation is multiplicativity. This is like not very clear why I should define in this way. First motivation is that I am able to prove that this sum complex is acyclic. Like this is already some motivation. Another motivation is that Goncharov defined a regulator map, and this regulator vanishes on these elements. So, like Goncharov regulator of this cycle is the following integral if my field is C. So this is some integral over x, something like this. So this is just for motivation. Yeah. So this integral of product of log and the log, and so this is clear that this integral vanishes on these multiplicative relations. Yeah. And so this is some motivation why we should like contract this subcomplex. Well, so. And we need to define in degree 0. This is not very important. The idea is that I need to prove that cohomology in this degree vanishes. So I need some cycle to prove it. But actually this is like truncation. So in general I should in any degree define relation in this way and conjecture expectations that this complex would be acyclic in any way, in any degree. But nevertheless I can prove that this subcomplex has no cohomology in this degree. Yeah, and so I can take quotient.
Should the right-hand 0 be a 2?
What?
Should it be MF2 instead of MF2?
MF2, yeah, 2. Thank you.
Bye.
Yeah. A lot of mistake here.
Just making sure.
Okay, maybe any other questions? Yeah, and so I want to state something even more explicit now. The following. So I will define the explicit map from block group to this quotient. So I want to recall. So this is curves in three-dimensional space, which are general with respect to faces. This group contains two types of relations, multiplicativity and antisymmetry. Yeah, I forgot to add differential. So before I also take quotient by the differential, but here I take quotient only by relations. So there is no differential here. And the map is very, very explicit. It just takes element generator from block group and map it to this algebraic cycle. So this is some particular curve in three-dimensional space. Yeah. So this is parametric formula. And this. Yeah.
That's Totaro, right?
Yes, this is Totaro's cycle. Yes, the cycle was written by Totaro when he proved actually that Milnor case theory is part of algebraic case theory. Yeah. And here is like explicit version of main result. It states that first, this map is isomorphism. So block group is like curves in three-dimensional space modular certain relations. But it is very interesting statement that it's turned out that actually I also should take a quotient by the image of the differential, yes, because like truncation. But actually image of differential in this group just vanish. So yeah, and this was like quite surprisingly for me. So, and the proof is not straightforward, like first I establish this isomorphism, then I define inverse map, take image of the differential, compute it in this group, I get certain relation in block group, and then prove this relation. And this shows here that image of the differential here vanishes here.
So this is only the first isomorphism, right, on the left-hand side, not the second?
Yes, the second is more or less obvious here. I don't want to talk here.
Okay.
Yeah, the second is completely straightforward. Yeah, and this of course implies this isomorphism here, because image of the differential just contained in this group. So I can drop it here. Yes, so like everything is very explicit. This is explicit, map is very explicit. However, to prove that this is isomorphism is not so easy. Yes. Yeah, and this map was studied before. Yeah, the were paper when it was proved that this map like well defined. It is also not trivial because we have Abel 5-term relation, and you need to check that it goes to 0.
And who did that?
What?
Who proved that before?
I think you.
Oh.
Okay. So now I want to explain the main trick, the main idea of the proof. First of all, I want to maybe you forgot what is the definition of this group, so I want to write it with generator and relations. Yeah. So generators, very simple, is cycles of this form. Yeah. Curve and three functions. But this is important that cycles should be admissible, general with respect to faces. What does this mean? That the cycle is general. Like intuition is that divisors of these functions should be disjoint. But it is not precisely true. Precise statement is that if some points lies on divisors of two of functions, then the third function should take value 1 at this point. So this definition is quite, well, it's difficult to work with this definition if you have some idea what should you do in higher Chow groups. Sometimes you want to write cycle which does not satisfy this condition. This is actually difficult to compute because of this condition. And on the other word, I want to say that the fact that we consider only admissible cycles is very important, because otherwise it's not clear how would you define differential, yeah? Because you just get cycle, not correct dimension, and yeah, everything doesn't work. But this definition, if you try to understand it from the point of view of algebraic geometry, is not very natural. It's not very natural condition that some rational function takes value 1, yeah. And generators is as follows. So this is antisymmetry relation, multiplicativity relation, and we have also reparametrization relation, because if we have some cycle isomorphic to P1, we can take, for example, elliptic curve, yeah, and parameterize this P1 by elliptic curve. So this relation shows that we can parameterize cycles differently. And yeah, and it can be proved that this is all relations. Yeah, so this is quotient of generator by relations. Yeah, and like surprising statement is that actually we can completely drop condition of general position here, and we get completely the same group. And like when I first thought about it, I like my thought was like, this is obviously not true. This cannot happen, but actually this is true. Yeah. So idea is just forgot about any general position. Yeah.
Where's the third relation coming from? You don't have that. I mean, the relations are just the generators of M, right?
Yeah.
So you only have generators from M1 and 2.
But one cycle can be parameterized by different curves, which maps to this cycle.
Okay.
Yeah.
Aha, I see. Thank you.
Even in differential geometry, we also have, like, you know, when we like compute integrals, you can change variables, something like that. Yeah. This is clear. Is this clear? Yeah, that we have such reparameterization. Okay. So idea is just forget about any condition of general position, and we have this definition. So generators are curve with 3 functions, like any non-zero function without any conditions. Divisor like can be any divisor. Divisors may be even the same. Yeah, and relations. So like antisymmetry relations, multiplicativity relation, and this like reparameterization relation. And the statement is that we get exactly the same group. So there is natural map from here to here. Yes, we can embed like admissible cycles to all cycles. And this is isomorphism. Yeah, and here, and yeah, and this is like the main idea maybe of why this proof works.
Sorry, what happens with cycles that have the wrong dimension?
What?
What happens with cycles that have the wrong dimension?
No. In this group, all cycles have dimension 1. The point that these cycles of dimension 1 can intersect faces not properly.
But I mean, if all the functions fi are all constant, for example?
Okay. Like if function is constant, you get cycle of this form, but this cycle is one-dimensional. If the image of my curve is point,
yes,
then this is 0 by definition.
Not by definition in this group.
No. There was a formula where. Okay, not by definition, but it follows from this relation.
Yeah. How?
Yeah. It can be proved. Actually, if one of the function is constant, then this is 0 in this group. It can be proved. Yeah. Some manipulation. Okay. Yeah, and this is actually connected with statements that like Belinson-Soulet invade 1. So like yeah. Okay. So this is isomorphism. Yeah.
So how the 5-term relation looks like in this group?
Yeah, I will talk about it. It is very explicit. The proof is very, very explicit. Okay. Yeah. So I very much like interpretation with colimit. So if we fix x, then these two relations describe explicitly like third exterior power of multiplicative group of function field on my curve. Yeah, exactly. Antisymmetry and multiplicativity. And then I have relations, then I like replace my curve. But this means actually that I take colimit over all curves. And this is definition of this group. Yeah, so this is just by definition of colimit. So I get the following presentation. This group is just colimit over all x. So here category is category of all like smooth projective algebraic curves, and morphisms are just non-constant maps. And if we have like this map from x to y, then we have pullback from function fields on y to function field on x. The only like thing that I need to divide on degree of this map. So this is colimit in very interesting category. This category is not like filtered or something like that. So it's not a priori clear how to compute this colimit. But nevertheless, it turned out that like, yeah. So this colimit it follows that this colimit coincides with just block group. Okay, so I want to say some motivation why admissible cycles and non-admissible is the same, why I can forget about this definition. So it's the following interesting statement. Let X be a curve. Then I can consider this group third exterior power of multiplicative group of function field on my curve. And it turns out that this group is generated by these tensors, so that Fi has disjoint divisors. This is very elementary statement, and I think this is it was very counterintuitive for me, because if two functions have vanished at the same point, multiplicative relations doesn't help too much. How can you somehow separate it? But here is example, not for 3, for 2. As this holds for any, you can, yeah. So we have the following two functions. The divisor of this is a minus infinity, and here b minus infinity. So they have the same point, common point, infinity. And then I write this relation, and you can check that this is actually true. And then divisor of this is a minus c, and this b minus infinity. So if a, b, c different, then exactly so, for these functions, the divisors are disjoint. And so I can apply this formula several times, and and I get this result. And this is main idea why this works. Okay.
For any C?
What?
For any C?
What do you mean by yeah.
C can be arbitrary.
Yeah, C can be any. Yeah. Yeah, and this explains why this map is surjective, because if function f1, f2, and f3 have disjoint divisors, then the corresponding cycles is admissible, and so we know that this map is surjective. Any element from this colimit can be obtained as image of admissible cycle. Injectivity also can be proven. Not only this is not only generators, but we can write relations, check these relations here. So. Okay. Yeah, and so to prove my end result, I need the following. So I consider this colimit. I have a map from block group, yeah, given by this formula, and it can be proved that this isomorphism. I want just to say that surjectivity follows from Galois descent for Milnor-Kay theory. This is some computation in spirit of Galois theory. You take some map from X to P1. We can assume that this map is Galois covering, something like that, apply Galois descent, so some computation. Yeah. So how much time I have?
2 minutes.
Yeah, okay, so it can be proved injectivity. I want to stay conjecture. Yeah. So conjecture, we can define this colimit not only for curve, but for any dimension. So I can take colimit over category of algebraic varieties of some dimension, and they alterations, that is a finite proper morphism of finite degree. Yeah, and so I can consider this colimit, and it turns out that one can define cochain complex where the differential is given by sum of residues map. I have no time to define, but this is something well known, defined by Goncharov. And conjecture is that this complex computes motivic homology of K theory. Yeah. And so statement is that indeed, if M is any and G is M minus 1 or M, then cohomology of this complex coincides with polylogarithmic complex and coincides with K theory. Yeah. And so conjecture is that we have this in any degree. This is here. Yeah, I believe that this can be done. Yeah. Okay. Thank you very much.
Thank you very much. Are there any questions?
And since you have a map between lambda, the lambda complexes and the whatever the gamma complexes.
I have a map from a polylogarithmic complex in any weight to lambda, and from high Chow groups to lambda. Yes.
Okay.
Yeah. So, like relations for polylogarithms satisfied in this complex, in this colimit. It can be proven. Yeah. For any weight.
Where do you use that the field had characteristic 0?
I used it. Well, I have certain like Galois arguments. Yeah, and so in like I use the fact that any extension is separable to apply some formulas. But I think like we can define norm map on Miller-Cass theory like for any field, and I think that something similar should work. Like I need more work, but I don't think that this is really yeah. Yeah.
So can you already prove for all M and J that for all J that the gamma and the lambda is the same?
No. This is.
But you also don't know. I mean, which you went from gamma to lambda and then to K theory? No.
Well, yeah, I can write it. So
maybe I misremember. My bad. Oh no, gamma was given by Bloch.
No, gamma defined by so Goncharov in any weight, yes. So this is polylogarithmic complex in weight M. Then I have lambda, and I have this Chow groups.
Yeah.
Yeah, and there is obvious map from here to here, and I so proved that there is well-defined map from here to here. Yeah, and conjecture that this and this, yeah, quasi-isomorphism. Yeah.
So how to relate the algebraic circle to the polylogarithms?
Algebraic cycles to polylogarithms. You mean if you have polylogarithm, how to construct algebraic cycle?
Or something.
Yes. So for dilogarithms, this was given by Totaro, and for like any weight, it was defined by I think in the paper Goncharov, Levin. Yeah, so they defined using some trees. Yeah, and you, yeah.
No, Bloch and Chris did it for classical polylogs.
And Goncharov, Levin, and you for multiple, yes. So for multiple polylogarithms, there are some like nice algebraic cycles given by like combinatorial formulas, something like that.
Do you expect that this lambda complex computes motivic
Yeah.
as well?
I don't know. Maybe no, but like. Well, I don't know. Maybe you need to invert something because you have exterior power. Because like Bloch complex, there is like alternating and non-alternating version, and I think the alternation version shouldn't compute integrally motivic homology. I think you should somehow replace this exterior power by tensor. But so I don't think that it's compute. Maybe you need to invert something. If you like invert some quite small prime numbers, then maybe compute. But yeah, I don't.
Your conjecture, should it be rational?
Yeah. I have conjecture. Yeah, it should compute. Yeah. But this is my expectation. Maybe not true. It's like, yeah. Why not?
Thanks very much.
Yeah, but there is some information.